In this video, I want to describe some interesting physical situations that involve magnetic field. And I'll just point out really quick, I want you to notice that I have not described any physical situations where we are looking at a magnet in a magnetic field. So far, we've only looked at electric charges in magnetic field. And I want you to be very careful to understand that the issue of electric charge and the issue of having a magnet are two different things. Not every electrically charged object is magnetized, and not every magnet is electrically charged. They are very different issues. And an important thing to figure out while learning about magnetic field and electric charges is the differences and also the similarities. Okay, so physical situations involving magnetic field and charge, not magnets. Okay, so I've got three that I'd like to describe to you. The first one is uniform circular motion. The second is called a velocity selector. And the third is called the Hall effect. So let's start with uniform circular motion first. So the ingredients for uniform circular motion, what we need is a uniform magnetic field. What this means is the direction of the field is the same everywhere, and the strength of the field is the same everywhere. You know that the magnetic field is a function of position in space. It can be stronger at certain places than others. But if I'm talking about a uniform field, then what I'm saying is every place in space has the same direction, and every place in space has the same strength. And that's what's called a uniform magnetic field. So we would say, well, it's just represented by a particular magnetic field vector, which is independent of location. So just some constant, right? So you can get uniform circular motion. It's the uniform circular motion of a charged particle if it travels, or if you put it in a situation where the motion of the charge Q, or actually, let me take that back. So we have a uniform magnetic field. So for example, let's consider the case where B points out of screen. The way people depict this is they draw these little arrow tips. So we'll say here is the magnetic field, and it's uniform because I'm drawing every field line. So these are actually field lines coming out at you, out of the screen. And you can see that the field lines are sort of uniformly distributed in space, right? The density of the field lines is constant, speaks to the constancy of the strength of the field. And everywhere you look in this coordinate system, the magnetic field points at you. So that's the uniform direction. So if I was to imagine a charge, let's imagine a little positive charge. At some moment in time, it's traveling with this velocity. So if you use the right-hand rule, then you will quickly see that if I study the force, remember the force vector is QV cross B. The charge is positive, so Q is a plus amount of charge. So V cross B and F have the same direction. And if you use the right-hand rule, you'll figure out that the force is down. So what's going to happen, you can see that the velocity and the force are perpendicular to each other. And actually that's by design. So the result, which is the force, is the result of the cross product of the vector v and the vector b. And what this means is F is perpendicular to v and F is perpendicular to b. That's what you get with cross products. The answer is perpendicular to the two input vectors, or the answer is 0. Okay, so here's the force vector, it's down. So what's going to happen is this force is going to steer the particle into having a new velocity. So let's update the location, right? It's moving towards the right, but it gains motion downwards, which means a little bit of time later, it's conceivable that it's moving like this. So it's got a new motion like this. All right, so here's the new velocity. And if you use the right-hand rule again, what you're going to determine is that the force is perpendicular to the velocity and to the magnetic field. You get this new force. And so as you update, what's going to happen to your little particle is it's simply going to traverse a circle. And that circle is going to have a radius r. And more than that, since F is strictly perpendicular to V, V cannot increase or decrease. So be really careful. There is definitely acceleration. It's actually called centripetal. It's centripetal. So let me spell it correctly. It's center pointed, right? The acceleration is in the direction of the net force. And so if the magnetic force is the only force, then the magnetic force is the net force, and the acceleration is in the same direction as the net force, right? So centripetal acceleration, right? But with centripetal acceleration, since the force is strictly always perpendicular to the motion, that what that means is that the motion can't increase or decrease in magnitude. It strictly only changes direction. So the motion, this is accelerated motion where the speed does not change. And this is called uniform circular motion. And there's some very basic relationships you would have learned in a mechanics class about uniform circular motion. In particular, it requires a centripetal force, so a center-pointed force, and it's related to the radius and the mass and the speed this way, mv squared over r. The centripetal acceleration, you just divide the m out of the net force, so it's v squared over r. So if the centripetal force is because of the magnetic force, then in terms of magnitudes, right, we have, right, the velocity is to the side, but the magnetic field points out at you, out of the screen, so there's a 90-degree angle. That is, the motion and the magnetic field are perpendicular to each other. So if we talk in terms of magnitudes, we're going to include a sine of 90 degrees. So I'm just going to include it as a factor of 1. So it's just Q times V times B. And that's the strength of the magnetic force. And it is the only force in the problem, and it is doing our centripetal accelerating. It's behaving as a centripetal force. And so if you just tack in the centripetal force relationship, then you've got this relationship here, and you can solve for the radius. So if I solve for the radius, right, so you'll multiply the radius up, divide by QVB underneath the mv squared, so you can see that there's a factor of the velocity that disappears. So you've got mv over qb, and this is a fairly basic, important result, right? it is associated with uniform circular motion, and you only get it if you have a uniform magnetic field. Also, yes. All right. So an interesting aside is, what if, actually, I'm not gonna do the aside. So yeah, here's the uniform circular motion result. Something that makes a lot of sense is R is bigger if M is big or V is big. So can you see that M and V are on the top? So if either of these values is bigger, then your radius of curvature is bigger. And that makes sense. Like, if your particle is moving faster, then a given magnetic field is not going to be able to divert or add motion perpendicular in a large way compared to how it travels, right? So if it's traveling really fast, but only under the influence of a certain magnetic field, right, then it tends to go further before its motion is changed much, right? So it goes in a larger circle. If the inertia is bigger, then a given magnetic field is not going to be able to divert a large inertia object quickly, right? So its radius of curvature is bigger. But R is smaller. That is, you get a very much tighter radius circle if you have more charge or if the magnetic field is stronger. And that makes sense as well. A strong magnetic field is going to have a very large effect on a moving electric charge. That is, it's going to wind it up into a really tight moving circle, or a tight circle, right? A small circle. Likewise, if there is more electric charge, a larger electric charge is going to feel a larger magnetic force. So you get a tighter circle, right? A smaller circle. Okay, so let's move on and talk about the next topic, which is the velocity selector. The next physical situation I want to describe to you is referred to as a velocity selector. And what this does is, you could imagine, it's actually a piece of technology or engineering. Let's say that you have some sort of source of particles, right? So here they all are. I'm going to imagine them positive. It's a little sort of natural to imagine them being positively charged. And I'm going to imagine them all having the same charge, although that's not necessarily necessary. But let's say it's a bunch of, say, protons, for example. But the thing is your source of protons doesn't necessarily give you all the same speed. So here is speed number 1, speed number 2. Sometimes it gives you a fast one. Sometimes it gives you one that's moving really slow. And sometimes you get these medium speeds, right? And I want to make a device, so a device that only passes or filters out, right? Passes particles moving with a specified speed. And it turns out that the way you can build one of these velocity selectors is by using crossed electric and magnetic, let me use the symbol, magnetic fields. But they are crossed. That is, E is perpendicular to B. It's easiest to imagine the situation with uniform electric and magnetic fields, so that's what I'm going to show you. So let's imagine that I've got a uniform magnetic field, and I'm going to draw the magnetic field in black, but the electric field I'm going to try to stick with using red. All right, so I've got electric field and magnetic field. So let me start by drawing the magnetic field to work with. So let's imagine I've got a uniform magnetic field that points out of your screen, right, pointing at you. It's uniform, so the direction is always only out, no matter where you check the value. And the density of these field lines is always constant, so the strength of the magnetic field is constant everywhere you ask. And the electric field, I'm going to draw it in red, is perpendicular to the magnetic field, but I'm going to draw it this way. I'm going to say that the electric field is uniform and points upwards. Remember that electric and magnetic fields are very different kinds of fields, but they both can put force on charged particles, right? Especially if for the magnetic field, if the charged particle is moving. So the electric field is in red, and the magnetic field is in black. And now let's imagine sending in a charged particle. So I'm going to draw a little blue positively charged particle, and I'm going to imagine it moving with a velocity v towards the right, which is, if you think about it, it's perpendicular to the electric field, it's perpendicular to the magnetic field, but I'm just going to think about this charged particle and wonder what kind of forces it experiences. So if I draw the particle here, right, let me draw first the electric force. So I'll draw the electric force on the positively charged particle. That's going to be the force by the electric field, right? And the force by the electric field, if you calculate it, what you need to know is the charge of the little particle, and also the electric field, right? The strength. And we know that it's going to be upwards because it's a positive charge and the field itself is up, right? So that's the electric force. But in black, let's think about the magnetic force. So the magnetic force is instead actually dependent on the speed, right? So there's a cross product and it's V cross B. And if you do the right-hand rule and figure out which way the magnetic force is going to be, it's actually going to be downwards, right? This you can get just by thinking in terms of the right-hand rule. So if you haven't learned how to do the right-hand rule, you are doing yourself a disservice. So go learn it now. Push pause on this video, go learn the right-hand rule. After you learn it or after you review it, come back, look at this diagram, and figure out why I can immediately draw this downwards arrow given all of the other information in the problem. If you don't do that, you're missing the point and you're not learning. So it turns out that after using the right-hand rule, you can say that in this case, our positively charged particle moving towards the right is going to feel a downwards magnetic force. So you can see that they're opposite directions. And we can get... So actually, let me change words. For a very specific velocity, the electric and magnetic forces cancel. And what this means is that the net force on our little charged particle is equal to 0, which means you get straight line motion, right? That's the definition of inertial motion, right? Straight line inertial motion, right? So if the net force is equal to 0, our object has no acceleration, so its speed and direction of motion do not change. But that's only for a very specific velocity. Lucky for us, that's what we want. We want something that gives us a very specific velocity. So if So how do we get these things to cancel, the electric and magnetic forces? So in terms of magnitudes, remember that the electric force is QE and the magnetic force is QVB, right? We know that the motion is perpendicular to the magnetic field, right? The magnetic field is out, the motion's towards the right, so there's perpendicular, so the sine of the angle is gone, or the sine of 90 degrees is 1, so there's just a factor of 1 from the angle. But F net equals to 0 depends upon, right, FE equals to FB in terms of magnitude. That is, the electric force and the magnetic force can cancel this way. And so if you just put in both sides, QE equals QVB, so you can see that actually the charge doesn't matter. It can be a proton, an electron, it can be any charge, right? Because it cancels on both sides, and the velocity that gets selected, right, is just E over B. This is the selected velocity. We can turn this on its head and say, let's say you want a certain velocity selected, right? Then what this dictates is you go and choose E and B, right, to give you your selected velocity, right? So, yeah, so this is how you create a velocity selector. You can imagine, right, since the magnetic force is the force that depends on the speed, if the speed is too fast, then the magnetic force is too big, right? You can see this black arrow is bigger than the red arrow. And so if the velocity is too fast, then it will divert downwards because the magnetic force was the thing that was too big. So this is too fast. But if V is too slow, then the magnetic force is smaller. The electric force is the bigger force, and the acceleration is this way. This is when your particle is moving too slow. And your particle goes in a straight line out the hole to where you want your particles to go, that you only want a certain speed. And these are the selected particles. So you just block the too slow, let them run into a piece of metal and get absorbed. And you block the too fast, they run into a piece of metal and get absorbed. But the ones that you select for, they just go out a little hole, just on a straight line from the source through your crossed fields, out a hole, and you have some selected particles. Your particles are all going to have the same speed, but they will not necessarily have the same kinetic energy or momentum. They just have the same speed. They'll have different momentum and kinetic energy if their masses are different. And that's an interesting thing. Yeah, okay. So it's a velocity selector. So next, I'm going to describe something that's a little bit complicated, but is actually associated with crossed electric and magnetic fields as well. The Hall effect is a really interesting effect.